All right. Today we study higher order partial derivatives of multivariate functions. In the case of a univariate function, we can differentiate it once to have the first derivative, and we can again differentiate it to have the second derivative. And we can do the similar thing for example, bivariate case. Okay, so suppose we have a function f of x and y, and if we differentiate it with respect to x, then we have the first derivative with respect to x. And if we differentiate it with respect to y, then we have the first derivative with respect to y, fy of xy. And for this function, for this first derivative, we can differentiate it again with respect to x. Then we have fxx xy. So this is a second derivative with respect to x and x. And for this one, again, we can differentiate with respect to y to have another second derivative, that is fxy of xy. And now for this first derivative with respect to y, we can differentiate it with respect to x. So we have fyx xy. Or we can differentiate with respect to y again to have another second derivative, that is fyy of x and y. So for a bivariate function, we may have four different second derivatives. And one important question is this one. So this is first we differentiate it with respect to x and f and y, and then differentiate it with respect to y, right? Is this equal to this one, fyx? That is, we first differentiate the function with respect to y, and then differentiate that derivative with respect to x. So are they equal or not? Sometimes they are equal, sometimes they are not. And we are going to study on which condition this equality holds. Let's see one example, explicit example. Okay, so suppose we have f of x and y as log, this is natural logarithm, x squared plus xy plus 2y squared. So suppose this is the function we are interested in. So if we differentiate it with respect to x, then we have, since this is a natural logarithm, x squared, xy, 2y squared, and 2x plus y. And differentiate it with respect to y, we have x plus 4y over x squared plus xy plus 2y squared. Next, we differentiate this one with respect to x. Okay, so that is fxx xy. By the way, this first x corresponds to this first derivative. This first derivative, and the second x corresponds to the second derivative. Okay. Anyway, so if we differentiate it using the quotient rule, I will just give you the answer. It should be, let's see, 2x squared 2xy minus 3y squared over x squared xy 2y squared squared. You should check, indeed, this is the answer. And similarly, we differentiate this one, with respect to y. Okay, just to be explicit. So this first x means the first derivative, and the second y means the second derivative. So we first differentiate with respect to x, and then we differentiate with respect to y. So note the order. So this is yx, but this is xy. So the order, this notation is a little bit twisted. But anyway, so if you differentiate this function with respect to y, you should have, I will just give you the answer. That is x squared 8xy 2y squared over x squared plus xy plus 2y squared squared. Okay, and next we calculate fyx. Okay, so we first differentiate with respect to y and then differentiate with respect to x. So we are going to differentiate this function this time with respect to x. Then the answer is, so let's write it more explicitly. So fxy, so this one is this one. So if you differentiate it with respect to x, the answer should be, actually it's the same as the previous case. So this is same as the previous one. So fxy is equal to fyx. And next, calculate this one. So the second derivative with respect to y and y. So that is, we again differentiate this function, this derivative, with respect to y. I will just give you the answer. It should be this, not 3, it's 2. Minus 4xy minus 8y squared. This. Okay, so in this case, these two second derivatives, cross terms, I would say, let's call it, fxy and fyx, they are equal. So let's write it down. fxy is equal to fyx in this case. So when does this hold in general? That's the next question. So our next question is, when does this hold? So in other words, when can we swap the order of differentiation of second partial derivatives? The short answer is, if these second derivatives are continuous, then we can change the order of differentiations. That's it. Very easy. So let's formalize it in form of a theorem. Okay, here's the theorem. Suppose f of xy is defined on an open region, U. Has the second derivatives, that is f xy and fyx. And these were also suppose they are continuous. Okay, so these second derivatives are assumed to be continuous. Then we have fxy of x and y is equal to fyx and of xy. So if there exist the second derivatives fxy and fyx, and if they are continuous, then we can swap the order of differentiations. Okay, let's prove this. We show that, let's see, we show that fxy of AB is equal to fyx of AB for every AB in the open region U. Okay, so this AB can be any point as long as it is in this open region U. Then first we take a sufficiently small delta. Take delta that is positive such that x minus a less than delta and y minus b less than delta implies x and y is in U. Okay, so this is always possible because U is an open region. Okay, so suppose U is something like this and AB is somewhere here. Okay, so if we take small enough delta, then we can pick a small square such that so this is delta and this is delta. Okay, so as long as x minus a is so the absolute value of this is less than delta and y minus b is absolute value is less than delta, that means x and y are within this square. Okay, and this square is completely buried inside the open region U. So if delta is small enough, this is always possible. Okay, so now let h and k be such that 0 absolute value of h is less than delta and 0 greater than absolute value of k is less than delta. Okay, and let us define this function f of h and k, which is defined by f of a plus h, b plus k, minus f of, let's see, it should be, let's say a and b plus k, and minus f of a plus h and b plus f of a b. Okay, then let's define a univariate function of y. Okay, it's y. Let's define this by f of a plus h y minus f of a y. Okay, so y is the variable, a and h, they are constants. So if we use this function, then f of h k becomes, so this part is u b plus k, right? So this is y is b plus k in this case. And for this part, that is minus, so this is a plus h, this is h, so this is u of b. Okay. Now, by assumption, so differentiating u with respect to y means a partially differentiating f with respect to y, right? So if we differentiate it, u prime of y, so that is f, this is the partial derivative of f with respect to y. by the definition of u, this is a plus h and y and minus a y. Okay, so now we apply the mean value theorem. So by the mean value theorem, there exists some constant theta between 0 and 1 such that we have this. So f of hk is equal to u prime of b plus theta k times k. Okay, so wait a minute, this one is equal to something like this. Okay, so this is b plus k and b. So if theta is between 0 and 1, b plus theta k is somewhere between b plus k and b. Okay, so by the mean value theorem, this is the mean value. And b plus k minus b is k, so that's this one. Okay, so this is equal to, so if we substitute this one to here, we have, let's see, so this k comes first, f y a plus h plus b plus theta k minus f y a b plus theta k, this. And next, let's define in a similar manner, let v of x. So this is a univariate function of x. Let's define this as, let's see, fy of x b plus theta k. Okay, then if we use this expression, then f of hk is expressed as k times, let's see, so this is b plus theta k, b plus theta k, and x is a plus h, so that is v of a plus h minus v of a. Okay, now we use the mean value theorem again. Okay, so by the mean value theorem again, there exists some, let's say, eta between 0 and 1 such that v a plus h minus v of a is equal to v prime a plus eta h times h, right? So if we substitute this one into here, we have f of h k. So this k times h times this one, v prime a plus eta h. But v prime is the derivative of this first partial derivative with respect to y, with respect to x. So this is equal to kh, let's see, so v, so f y x a plus eta h and b plus theta k. So this is it. So this v prime is the derivative of this one with respect to x. So that's, so here we have this one. Okay, now let's review what we have done so far. So first we introduced a univariate function of y as this. Then by using the mean value theorem, we derive this one, and then we define another function of x, and again using the mean value theorem, we arrived at this expression. So f of hk is given by, in terms of the second derivative, fyx. Okay, so we do this process again, but first we differentiate with respect to x instead of y, then do the same thing with respect to y instead of x. Then, by a similar process, similar procedure, there exist some theta prime and eta prime. Both are between 1 and 0, so we use the mean value theorem again. The same f of hk can be expressed as kh and fxy instead of yx. So, and a plus eta prime h and b plus theta prime k. Right? Same logic. So the same function f of hk can be expressed in two different ways. So this one and this one must be equal. Okay, so kh fyx a plus eta h and b plus theta k is equal to kh, and fxy a plus eta prime h b plus theta prime k. And k and h are non-zero, so we can just divide both sides by this, and we get this equality. Okay, we're almost there. Now, we want to get rid of these parts, right? But we can take the limit. Limit. H and k going to 0 and 0. Okay. By the continuity, by assumption, assumption, we are assuming that this and these two second derivatives are continuous. Okay, since they are continuous, fyx and a eta h and b plus theta k, this will converge to fyx of a b, and fxy a plus eta prime eta prime h b plus theta prime k, this will converge to fxy of a b. So they are equal, and we are done. Next, we consider even higher order derivatives. Okay, for example, if we have a function f of x and y, and suppose this function has second derivatives, such as fxy or fyx. Of course, if these are continuous, then they are the same second derivatives. And these can be differentiable again, so that we may have the third derivative of these. For example, there are many kinds of third derivatives, but if we, for example, if we differentiate this one with respect to y, so if we differentiate this fxy with respect to y, then we have fxy y. And if we differentiate this one with respect to y, yx, we have fyxy. Okay. But if these two second derivatives are equal, then these third derivative should be equal. Okay, so fxyy should be equal to fyxy. Okay, so let's write it a little bit more explicitly. So this is equal to, so okay, let's write like f of fxyy is this. Y, let's see, y and x. Okay, so this one we write like this. So we differentiate 3 times. So we like 3 here, and y is repeated twice consecutively. So in this case, we write something like this: dy squared and dx. Okay, and for this one, we write fyxy is this. So this y corresponds to this y, and this x corresponds to this x, and f. And this y corresponds to this y. Okay, in this way we write d3f dy dx dy. Okay, so if the second derivatives are equal, then these third derivatives are also equal. By the way, we usually write something like this to mean the second derivative of fxx of xy. So 2 comes here in the numerator and 2 comes here in the denominator. So don't get confused. So this is of course same as this. xx. So instead of repeating this, we write something like this. Finally, let us define some terminology, some technical term called functions of class Cn. Of class Cn, okay? So we say function f of xy is n times continuously differentiable. Differentiable or of class Cn. So what this means is this. If f of x has all the partial derivatives, up to the nth order. So this is differentiable n times with whichever the variable. So either by x or y, x and y, and all of them are continuous. So all the derivatives up to nth order are continuous. So this is, in this case, we say n times continuously differentiable or simply of class Cn. And similarly, we say f of xy is infinitely differentiable. Or of class C infinity. So this means this function has all derivatives, all partial derivatives of any order. Of course, on the domain U, right? So in this case, we don't say continuously, because if it's infinitely differentiable and differentiability implies continuity, then it all automatically follows that they are continuous. And also in this case, we also say this function is smooth. Okay, so this is a special way of saying the same thing. It's infinitely differentiable of class C infinity or smooth. They all mean the same thing. And it is easy to see that if, for example, f of xy is of class C3, then we have fxxy equal to fxyx equal to let's see, yxx. In other words, we can use any order of differentiation to get the same third order derivatives. And that's all for today. See you later.